Thanks a lot, everyone, for joining this tinyML talk. I'm super happy today to moderate this talk, which is about unsupervised federated learning. My name is Senthil, and I am a technical product owner, algorithms at Bosch Consulting, Bengaluru, India. Today, I have a pleasure to introduce Dr. Ranjitha Prasad, who is an assistant professor at Indian Institute of Information Technology, Delhi, and she's going to talk about unsupervised federated learning. Before we start the session, I would like to thank all the strategic partners who are making these events possible. I would like to thank AZIP, Unlock Devices, Arduino, ARM, BrainChip, Edge Impulse, Efficient, Greenways Technologies, Gravity Incorporations, HiMax, IBM, Imagimo, Infineon, Inatera, Microsoft, Nota AI, NXP, Polytechnology, QZO, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, ST Microelectronics, Synaptics, Syntient, and TTK. Thanks to all our strategic partners. Moving on, I would like to talk about tinyML community's online presence. It's growing really big. In Meetup, we have around 70,000 members in 49 groups in 41 countries. Parallelly, we also have a presence in LinkedIn. Please do subscribe to these channels and groups where we will be constantly updating on the upcoming talks on the recent trends in tinyML. We also have a presence in YouTube channels where all the presentations and tech talks around the globe, including this one, will be uploaded. In the next slide, can you go to the slide, Ranjitha? Yes. So we have around 10,000 subscribers and almost around 600 videos with 376 views, 1,000 views. Please do give it a try. You can see all the recent talks and interesting ideas which is happening in the tinyML community. The upcoming events, I also want to talk about an upcoming events. We have a tinyML Asia Technical Forum, which is going to happen in November 16, 2023 in Seoul, South Korea. Please do register for this event. The registration is still open. You can present your technical topics and also a demo to this technical forum. We have an URL here and also the QR IDs. We have HAA Technology Report 2023. We can download this technology report from vevolver.com. So this technical report will list down all the state-of-the-art technologies in hardware and software related to HAA. Please do give it a read. It will be interesting. As a reminder, this video, this technical talk and the slides in this video will be posted tomorrow in YouTube channel. For the participants, if you have a question, please use this Q&A channel and add your queries. I will take this Q&A questions and at the end of the technical talk. Again, I'm pleased to introduce Dr. Ranjitha Prasad. Dr. Ranjitha Prasad obtained her PhD from the Indian Institute of Science in 2015. Her experience is in the general areas of signal processing, Bayesian statistics, and also more recently in machine learning and deep neural networks. She has been a postdoctoral researcher at Nanyang Technical University and NUS Singapore. And she was also a scientist at TCS Innovation Labs Delhi. Her current research interests are in causal inference, explainable AI, and federated learning. Over to you, Ranjitha.
Thank you, Sendil, and thank you for so many participants for joining from all around the world. So let me just quickly switch to, probably I'll just share again. So welcome to this talk. I'm going to give, in fact, not slightly formal, yes, but more of a discussion kind of a talk on unsupervised federated learning. This is something that caught our attention when we started investing more time in federated learning. I think, so the way this talk will proceed is that I'll first introduce you to federated learning. Many of you may be aware of it, but this is going to be a quick introduction, of course. And then we'll go into this whole aspect about unsupervised federated learning. Here we'll look at some existing method and we'll talk about a particular approach that we have proposed. and show some experimental results. But in the process, my goal is to sort of raise awareness about the actual issues in federated learning. Why exactly do you need unsupervised federated learning methods, and so on, right? So before I actually go into, thank you, Sendil, for the introduction. But very little introduction of what I did after really joining IIIT Delhi. So I joined IIIT Delhi as an assistant professor in end of 2019, pretty much 2020 to start with, right? And that's when COVID hit. So it was pretty much my lab was we all sat in our own houses, and Intelecom lab was formed. Fortunately, being here for the last 1.5 years, we've been able to still work together as a lab. Our research interests are mostly in federated learning. Most of my students work on federated learning. We also look at areas like explainable AI and causal representation learning. My research group currently has about 4 PhD students. In fact, today the work I'm going to talk is partly MTech thesis and majority of the work done by a PhD student in collaboration with an industry partner. And I have MTech students as well as BTechs. Our lab is funded by several government agencies. DRDO DYSL AI labs are one. And it's also the Department of Science and Technology, SUB, and MEPI. So these are all government organizations in India. So what's federated learning? I think most of you, I think many of you are familiar, but I just thought a talk like this should start with the introduction to federated learning, right? So why do you need federated learning? So each of you, I'm sure you use phones, you use several devices where we as people, right? We populate data, right? So we generate data. There are many apps, onboard sensors, etc., which collect data. And typically, if you want to train a machine learning model, then we have to actually collect or put all this data together and then send it to a central entity. You call it a cloud, you call it a server, and then that's how. And then you have the parts of training and inference and so on, right? That's how a machine learning model would be trained. But the main question is, will all of you really be comfortable sending, say, your pictures onto a cloud? We do it right now, but if given an option, perhaps I would prefer to keep my data to be private, right? So perhaps it's not a very big deal if it's about pictures or messages, but think about hospital records, right? So or think about several high security applications. Of course, privacy is a very big concern, right? No, edge users, as we are called, as different entities are called, these edge users would not like to share their data with a central entity, right? So instead, what can be done? So what can be done is I can train my own model, right? The edge users can train their own models and only share model updates. Okay, so when I say model updates, for now, you can think of it as some meta information about the model can be shared with the central entity, or what I call here as the federated server, right? So we share some meta information from each of these client or edge nodes. And using this information, the federated server can actually come up with a ML model, right? So what's the advantage of one such ML model? Because it has updates from all these so-called clients or edge users, it's possible that this ML model is more generalized, right? It actually has a better test error for unseen data that may come from the joint distribution of all the data and all that can be there in any of the edge users, right? So typically, a very popular setting here, or a popular algorithm here, is what is called as federated averaging. That's what I'm depicting here on the right side. What we say is you train, say, every edge user can run can run SGD, right? Locally, right? So we have a learning rate eta local at the edge user, and you compute gradients on your own data, right? Because K here represents my own data, and later I come up with certain updated parameters at the local client end, and these parameters are now sent, right? So the data aspect would have been if I actually send the data set itself, but instead we're only sending the parameters. And once the parameters are sent to the server, what does the server do? It simply takes all the parameters, assigns some kind of a weight. Okay, so how do you assign the weight? It could be that it could actually assign some of the edge users to be more important than the other, and average of all these weights now forms a global model. Now this global model is broadcasted back to the client, and now the client resets its model to the global model. That is, this particular theta t plus 1 k comma s would be now theta t plus 1, which is the global model, right? So with this process, if it continues over a certain number of iterations, or what we commonly call as communication rounds, we see that it achieves convergence. In fact, there are theoretical proofs for that, many of them. One of the first papers to do that was this paper called on the convergence of federated learning in non-IIT settings, right? So there is a sublinear rate of convergence, which is usually there for SGD, that has been proved even in the federated case. Okay, so that's briefly about federated learning. So should I take questions right now, or sorry, Sendil, I'm a bit confused. Should we? So there are some comments on the chat in Q&A. Should we take that now, or should we take that later?
Yeah, we can take it at the end. If it is something very important which stops the presentation, I will ask those questions. Yeah.
Sure. Yeah. Okay. So so far so good. What are the advantages of FL? It's the main reason why it really came up is data privacy. Collaborative learning is something that it offers. It can learn from diverse types of data, right? Now think of a case where there are different machines collecting different types of data, right? So you can actually learn from diverse kinds of data because of the non-IID assumption that exists, which says that the data need not really be homogeneous across the clients. We can think of some real-time continual learning type of settings. There can be efficient hardware utilization, because now it's no longer essential that all data needs to be handled at a central location. And of course, there's also scalability, right? Applications of FL, there are many. I mean, just type it on Google and you'll see it's been applied at places where you would not even imagine that can be used. Healthcare, vehicular networks. I mean, this list doesn't really do justice, but I just put it for the sake of it, right? Okay. So what are the challenges in FL? Typical challenges in FL, so there is always going to be a type of trade-off between how many times you communicate with the server, right? Say you have N clients, how many times will the N clients communicate with the server? Because every communication has some communication overhead involved, right? So, and locally you will be doing several SGD, you'll be taking several SGD steps. So there's always going to be a trade-off between should I take many local epochs or local SGD steps as against doing global updates, right? So global update would mean there's a communication overhead and I pay somewhere else. Whereas just doing local learning means that I'm not actually generalizing my model as much, because I don't get the information that from the other clients in terms of parameter updates, right? So that trade-off always exists. Another major issue is that of systems and data heterogeneity, right? When we say system heterogeneity, what it essentially means is that different systems have their own computational capability, and one could learn slower than the other, which means that the bottleneck in the entire system would be the slowest device, right? And data heterogeneity would imply that if you have very diverse data at different clients, then how then would it be possible to actually obtain a good model at the server, right? A good global ML model at the server. Here, I should also say that personalization is often a goal. It's also a goal for us, where we say that not only should the federated learning system be able to handle diverse data, but to give a good global model, but also give good local models, right, which work well on the data that you see. It's not so. If you think of a federated averaging system, then it says that the parameters at all the clients are same as that of the server, which means there is a common ML model across the entire system. But that may not be the goal, right? We want different ML models at each client, because the type of data that we see can be vastly heterogeneous, right? And of course, there are privacy and security concerns. I won't go much into this here, but something to note. Okay. Why is I sort of already mentioned this, but why personalization, right? Basically, it's all about data and model heterogeneity, right? To address heterogeneity, it's essential that we not only cater to the global aggregation aspect, but also to the local data that we see, right? So what we expect is there should be improved convergence on heterogeneous data. And also this should be a local solution as well, right? It's a personalized solution, and it tackles what is called as client drift. Very quickly, what is client drift? What we see when you expect that the parameter estimates, here represented by W1 and W2, would actually be close to what would have happened if there was this kind of an average client, right, whose data was probably some kind of an average of all the data that you would see. Whereas this won't happen if there is a non-IID data. So when we say non-IID data, we mean to say that the distributions at different clients are not identical, right? And in such a situation, it so happens that as the communication rounds proceed, it's highly likely that the parameters at the clients actually is much farther away, and W2 star is sort of closer, which would not have happened in the case of IID, IID samples. So client drift is a very popular issue in the presence of heterogeneous or non-IID data. And this is something that personalization usually addresses. Okay. So when we started our research, we of course, we went through some of the less addressed or less explored terrains in federated learning. And to me, these two aspects really make a very, very big difference. Okay, so, or rather, they motivate me to actually work in this area. Although I'm mostly focusing on the first area in this talk, I'll also just introduce you to the second area. It's something that is very close to my heart, and we're trying to work in that. Let's see if we are successful. So the first area is what is called as unsupervised and personalized federated learning. The first question to ask is, if you think of something like federated averaging, which is one of the most popular methods in federated learning, these methods are actually supervised learning methods. Okay, so which means that you are expecting that data at the edge is actually annotated, right? The data at the edge is labeled. So, so what does it mean? So if I want to run machine learning on my phone, it means that I might have to actually sit and annotate certain data points, right? Or I need to use some kind of help, right? It could be another app, it could be something else which would actually annotate my data. if you think of any other help that would actually try to annotate data, the first question that comes in your mind is, isn't that itself privacy, restraining my privacy, right? Privacy compromising. So given privacy constraints, expecting that data be labeled at the edge itself is somewhere a wrong assumption, right? You could still come up with many use cases where data can easily be labeled. Perhaps machine level labeling can be done, but you can also come up with many applications where labeling of data at the edge is a problem. Okay, so that is why unsupervised methods make huge difference, right? I mean, that's actually the direction in which I would say federated learning should try and move. On the other hand, data heterogeneity is a real problem, right? So you would definitely want the method to be personalized as well, because every device is going to be seeing vastly different data, which means that finally personalizing models for every client is the key. Okay? So unsupervised and personalized techniques, whether they can be done together or not, that's another question to ask. But this is definitely something that is very crucial in federated learning. The other question is, do you think Bayesian methods for personalization actually do well, right? When I say Bayesian methods, what I mean is, I'm not sure how many of you are familiar with that here, so let me not go very deep into it. But usually Bayesian methods don't really give you a single estimate of parameters, right? It actually gives you a distribution of parameter estimates, and it's usually very advantageous where you expect limited amounts of data, right? So we do expect that client data is limited, and hence any machine learning model or deep neural network model that you try to associate with the client is going to overfit. And that's where a method like a Bayesian method could actually help. Another direction in which our lab is actually looking at is the incremental learning aspect, where again several Bayesian methods are very much helpful, because in Bayesian methods we usually learn that's what I'm trying to show here in the picture. You actually have a prior belief. Every time you encounter data or what is called as evidence, you actually come up with a posterior belief, right? So this posterior belief can be carried forward to help perform incremental learning or design incremental learning methods. So these are two areas which I think are not as explored. I mean, there are some methods, of course, but not as explored in federated learning, but definitely need to be looked at in my. So now let's come to unsupervised federated learning, the actual crux of the talk. So the big question is unsupervised learning also, I mean, is it really possible? Why do we ask this question? So typical unsupervised approaches include methods like clustering, PCA, or representation learning. So you could have autoencoders or you could have VAs. So remember that we don't have any information on the labels, right? That's the unsupervised domain, right? So now, if all the data were to be present in one place, you could still think of a representation to be learned, and there is really no so-called clash in the representations that may be learned by different clients. But here, different representations, or if you're thinking of clustering, that's also in a way a representation, right? Different types of clusters could actually be learned by each of the clients. So then how would you actually put them together? In supervised learning, what happens is, because you have the labels, there is some sort of a guiding light for us to put all these representations together, right? Or in that case, the models itself together. But here we don't have any such information at the central entity. Okay? So that means, how do you think you would actually, I mean, don't you actually intuitively feel that there is some information that is going to be missing when you try to do unsupervised federated learning? Okay, so that's why the fourth question: is there truly unsupervised method. Okay, so my answer, unfortunately, for now is going to be around no. We've not really seen a truly unsupervised method. There is some kind of an help that every unsupervised method thus far in literature actually tries to take, right? So for example, if it's clustering, you may need some information about the centroids. If you're trying to do representation learning for a downstream task, which is maybe classification, then you may want to know a little bit more about the class priors, etc. Right? So some side information is usually given. Okay, so our thought process is also somewhere around that. We'll soon propose our method where we actually go for federating an autoencoder. But we also saw that some kind of a guidance is usually required when we try to train and infer from these methods. But let me just introduce you in general to about two or three methods, which were probably the papers that started any work in this area. So I'm going to talk about three methods. One is called FedU, the other one is called FedX, and probably the most relevant baseline right now when we talk in terms of numbers with accuracy numbers is what is called as orchestra. These three methods were probably the most important methods because either they were very early in this field or they sort of report the best possible numbers. So FedU, as I already mentioned, actually depends upon the class priors. Okay, so here the assumption is that exact labels of so basically here the assumption is that a data set comes in as sets of what are called as sets of these smaller data sets U, right? And what they assume is that the data distribution of each of these U is somehow slightly known. It's not completely known. They don't really assume the labels are exactly known, but the class priors involved in this U data sets are available. And from there, they prove many theoretical guarantees to say that to say how they could actually pseudo label the samples and then use exact federated averaging type of an architecture and still come up with good generalization capability at the central entity. Okay, so these methods are not personalized. That's one more thing to remember. These methods still try to come up with the same model across the clients and the server. Okay, and FedX, on the other hand, is a distillation type of a method. In fact, I would say that perhaps this actually requires the least amount of side information. In fact, FedX works on two types of losses. One, so there are two levels of knowledge distillation. One is what is called as local knowledge distillation, and the other one is called as this global knowledge distillation. Local knowledge distillation, it actually minimizes this embedding similarity. Basically, they use a contrastive loss, and this is done for the local data itself. So once that is obtained, they use federated averaging to actually just put all the model weights together, right? They take an average of all the model weights, and now because of that model, they actually have a global they have an alternate view of the same data, which is actually got from the global model. And using this, they also have a global contrastive loss. And they see to it that, when it's contrastive loss, it's the same approach, right? You try to maximize the agreement between views of or the augmented data points of the same of a given instance, and you try to minimize the agreement between the different views of different instances, right? So it's the same logic of contrastive loss. So what we saw is that FedX results in very poor representations. So it turns out that if there was the error sort of keeps getting propagated once you try to introduce a little bit of data heterogeneity, that sort of propagates, and FedX usually results in very poor accuracy numbers. And finally, we have orchestra. Orchestra is a clustering approach, right? So what they say is that the goal is to orchestrate. So the paper is written really well. The goal is to orchestrate a global partitioning of data, and then compute a set of servers, set of centroids at the server, and then the server is actually going to dictate or instruct the participating clients to use these centroids, right? So that's a very natural thought process, because otherwise each client can cluster on its own and have its own centroids. So even any clustering algorithm actually requires some kind of guidance on, say, the number of clusters, etc., when you start the clustering algorithm. That is the point where orchestra takes the server in the orchestra takes every client to and gives it a set of centroids to train upon. These centroids also can change over the rounds, and they also have some augmentation that they do to sample these cluster assignments. So the results in this paper have this inherent assumption that the data actually can be clustered, right? So if the data is very heterogeneous, and although they actually have quite good results even in the case of heterogeneity with respect to the class labels, our own assessment is that perhaps they may not be able to handle if certain clusterability does not exist among features. Okay? So now let me come to the method that we have actually proposed. We've just sent this paper, of course. So what we think is that for an unsupervised method, representation learning is the key, right? So we need to learn representations that actually suit certain downstream tasks, right? That's where unsupervised learning method is very useful. So the first question we asked is, can we federate an autoencoder? Okay. So of course I should give the credits first. This was done by my MTech student and Kanika, and alongside a PhD student, Nazreen. And we have industry partners from Lightmetrics Limited, Private Limited, Bangalore, Ashish, Mithun, and Krishna. Special thanks to them as well. So this is the kind of output we were able to get, and this was actually our motivating point. If you have a simple autoencoder at every client, which you take through federated averaging, then this is the sort of representation we get. This is the overall overall representation that we get. Using orchestra, we saw that it's slightly better. We could still see some clusters. So these are actually the classes that are there in the CIFAR 10 dataset. We could see some distinction in classes, but not as much. But with our method, we could actually see that the classes were clearly being separated, and it's actually able to learn the representation. So what was the information we gave? So just hold on. I'll soon discuss that. Idea is very simple. Let's work with very simple examples. Let's say that I have some quadratic laws, and I have some representations which are linear invertible representations, right? So it's as good as just multiplying with a matrix, right? So essentially, X can be written as some, so like I write it here, Xi hat, right? So remember what an autoencoder is. Autoencoder takes Xi to some latent space and then to Xi hat, right? So which is the reconstruction of the input itself, right? It's an autoencoder, so there are no labels. And finally, what we do is we look at the difference between Xi and Xi hat square. The squared sum of squared over all the samples is actually how the loss is computed, right? Of course, this is a special case of quadratic loss. You could have other losses as well, but let's just stick to the quadratic loss for now. Now I'll write Xi hat as AB times Xi. This is a very simple case. I'm saying that both encoder and decoders, they are actually simple matrices, right? So let me just take this A outside and get something like this. right? So you can easily see, I'm assuming that this is an invertible projection. So I could have a inverse xi and I'll have a bxi. Now, this A inverse xi and bxi, if you think about it, in fact, these are exactly the latent space representations, right? So one of them is actually zi, and the other one is actually zi hat. And I get xi minus xi hat the whole squared to be smaller than mod A. So applying the Cauchy-Schwarz inequality, I can see that the squared on this is actually smaller than this quantity. Now, mod A squared typically is something constant. It depends on A. And this is simply zi minus zi hat squared. So I have a bound on the loss that we compute using zi minus zi hat squared. If I simply add xi minus xi hat squared to both sides, I have this bound on the quadratic loss, which says that I can actually compute the quadratic loss as a sum of your reconstruction loss and the sum of the loss as dictated by the latent vectors, right? So we extend this to nonlinear transformations as well, right? So I'll call one of them to be local. Why is this local? Because I have x and x hat at the local devices, right? So I can compute this locally. And I call the other one as global. So let's see why this is global. So essentially it means that if I share z's with the server, okay, what is z? Z is my latent space representation. So from here, we get inspiration for a network like this, where I say that my encoder is there at the client, right? And I send this encoding Z to the server. I send encodings from all clients to the server, which means that now server has some encodings to train on. It's not easy to come back from this encoding to the data, right? So that's why we still can have a certain level of privacy ensured here. And then we train a decoder at the server, okay? So which means that I have a xi here and then I have a zi that goes in and becomes some y, right? I mean, I don't know what this y is. It may not be xi hat. But remember, I need to still compute my losses, which means that I need an xi hat at the client. So to enable this, we actually add a surrogate encoder at the server and a surrogate decoder at the clients. So what happens to y? Y actually goes on to become zi hat, and this zi hat is actually given back to the clients so that they can now compute their x hats, right? So the way the entire network works is at the client, we minimize this loss, xi minus xi hat, and at the server, we minimize the loss, zi minus zi hat. And that's exactly what we've written here under server and client updates. So GS is actually the surrogate encoder at the server, and and HK are the surrogate decoders at the clients. And these are now the losses that we minimize. Okay, so this is a slightly more mathematical view of the same idea. So what do? We have some X data at every client. So this has X1, this has X2, and this has, say, XK. And this XK goes into an encoder and a surrogate decoder, and the loss is computed. And it gives these encodings, or it gives these latent vectors to the server. So everybody give their latent vectors to the server. The server trains its network and minimizes the loss between Z and Z hat, and then provides back the reconstructed Z to the clients, right? So this is how we achieve federating an autoencode. So before I go ahead, actually, if there are any questions, I can take it, because this sort of...
Yes, Ranjitha, we have one question, like two questions. The first one is on what is the difference between a federated learning and a transfer learning?
Right. So yeah, these are actually very different concepts, right? In fact, transfer learning in a way assumes that you've already seen some data, in the sense your network, right? Your network has already seen some data. It's actually learned from that data, and now you transfer that knowledge onto a new when you're learning a new data set, right? When you're learning, or rather or on inference on a new data set. Federated learning essentially means that actually I don't see if it's an edge user, we don't really see data from any other client. In fact, that breaches the privacy constraint. On the other hand, server sees updates from all the clients at the same time. So there is, of course, you can implement it as a transfer learning model. You can implement it, but essentially the basic model for which at least convergence guarantees are available would be where it's not a transfer learning approach, right? It's where all the parameters get updated at once, right? So did I answer the question?
Yes, I think yes, we can.
Okay, so yeah.
There is one more question. I think it is based on the slide number 11 to 13. I think you gave one example.
Okay. 11 to 13. Yeah. 11. Okay, yeah, this one. Yeah.
So the question is about like, is this example similar to a self-supervised learning methods? And how is it different from
Right.
like
So
federated learning, unsupervised federated learning?
yeah. So self-supervised is closely related because they also don't really use labels, right? So they actually form our baselines. But unsupervised actually is very different from self-supervised as well, right? Unsupervised maybe even for example, yeah, I mean, I think the basic difference that exists between unsupervised and self-supervised sort of gets carried over here as well. So we do compare with these methods, but it's not exactly the same because these are unsupervised. That's how it is. Yeah.
Okay.
So there's one more, I think. So Vinay is asking, how is the latent space Zi from each client be used to get the error as Zi minus, as I assume reference latent vector is not unknown to the server. So Vinay, so the way you start it off is you actually pass the encoded vector, right? Which means the latent space vector to the server, right? So that forms the initial data for the server, right? So now server has some data to train on, and there also it has to be unsupervised, right? Because I don't have any labels there, which means that it'll actually try to simply go from Zi to Zi hat, which is your reconstruction of Zi itself, right? Now, how is that guided? That actually the guidance comes because of this entire loop, right? So that the further encoded vectors, right, Zi hat, go back to the clients. Now the clients compute the loss there, right? If that loss is high, it means that the server is actually not going in the direction of the data that exists at the client. So the loss computation at the client indirectly actually affects the loss computation at the server. So they both work collaboratively to actually bring those losses down. And and we've seen that actually the loss goes down with a number of rounds. Yeah, I hope I answered your question, Vinay.
Yes. So basically, it's a loss function. My understanding is loss function.
Two losses,
Translation
which
happens at the client side, so there is no need for a server to know the details. Okay.
Right. So it's two losses.
Thanks,
which actually keep on decreasing each other. It's like that.
Yeah. Thanks.
Okay, so should I go ahead or should I wait for this? I got some feedback poll. I can go
think
ahead.
it's a follow-up from Vinay. He is asking, is loss function at each client need to be same?
Need to be the same. So not necessary. In fact, loss function just needs to give these latent vectors zi's, right? So any function, at least as a concept, the loss function can be different. But frankly, we don't really have any result to show that. In the sense, we don't have a theoretical result to show that it could be any loss function. But as a architecture, it can still use any loss function, which gives me one such latent space representation.
Okay.
Yeah.
Yes, thanks, Ranjitha. We can go ahead with the presentation.
So, okay, so I have about I think about 10 minutes or so. So I'll quickly talk about the evaluation strategy. So our evaluation strategy is largely inspired from orchestra. I think that actually has some of the really good evaluation methods as compared to any other paper in the literature. Excuse me. So the first method of evaluation is what we call as linear evaluation, where we evaluate the representation that is learned in a standalone manner. So what we do is we still use accuracy as the metric. So we train a classifier by freezing the backbone. So when I say backbone, by freezing the representation and only training the classifier, right, on both local test data as well as global test data. Okay. So we consider about 10% of the data for classifier only classifier training. So we don't really train the backbone. This is what is called as linear evaluation, because we expect that the data actually passes through the representation and then trains the classifier and also tests the classifier on local and global test data. And on the other hand, there's also something called as semi-supervised evaluation, where for the first about say 100 epochs, we actually allow the classifier to also change the backbone. Okay, if there is some updation of backbone, then for about another 100 iterations, you just train the classifier. 100 epochs, you just train the classifier, and then you see the accuracy. And then to simulate heterogeneity, there are different methods that are there to simulate heterogeneity. So the types of data sets we use are something like CIFAR 10 and CIFAR 100, right? These two are, MNIST used to be one of the favorite data sets earlier, but frankly, numbers on MNIST are so high already that you can't really show any improvement if you really want to, right? They've already touched 98, 99, and if you're touching there, you really cannot show any improvement. So CIFAR 10, CIFAR 100 is definitely somewhere where you can try and improve on methods. It's good to have two types of such data, because CIFAR 10 has only 10 classes, CIFAR 100 is 100. So in some sense, this kind of a class imbalance, etc., the contrast can be shown quite well. So usually the way to simulate heterogeneity across clients would be to provide different, say a scenario where you give 3 classes to the first client and 3 classes to each of the clients, right? 0, 1, 2 to one client, 3, 4, 5 to another client, and so on. So that's one way of, because that makes your classes imbalanced, right? So you have to just filter out in the original data set and split the data set according to the classes. The other way, there it is a very strict partitioning of classes. Okay. The other way to do it is have something called as Dirichlet-based class imbalance. This is a slightly more softer way of introducing heterogeneity, because this actually changes the distribution of classes in each client, right? So it may so happen that in one client, there are 10,000 samples of one class and maybe just 1,000 samples of another class, and so on. And some classes may also be missing. In another client, there is a different distribution of these classes. And this kind of class imbalance is more recently, it's been preferred in papers. So there's also a paper saying that this is this is sort of correct as compared to the strict class partitioning. And we actually show results for both, but primarily we use Dirichlet-based class imbalance to simulate heterogeneity. The trick that we actually required finally to make our method work well is actually pre-training. We had to pre-train our encoders. We use mini ImageNet pre-training for our encoders. So like other methods, we also face the problem that the direction that is picked up by a training initially, right? That really doesn't go in the right direction. So we saw that in multiple runs, sometimes it would actually go to a good representation and sometimes it did not. But when we pre-trained the encoders and the classifiers, okay, so classifier is outside this backbone training. So we're not worried too much about pre-training the classifier, but when we pre-trained the encoders, it definitely helped us get a good representation. So in some sense, I would say even we were not exactly unsupervised, but we did not use the same data set, right? So that way we still did better. We did not actually require anything from the data set itself. Okay. So this is the set of numbers that everybody shows. We have also just put it here. But more interestingly, we managed to do better than Orchestra on CIFAR 10 and CIFAR 100 datasets, and the rest of these are actually self-supervised methods, right? SimCLR, the basic one that uses contrastive loss, and then the Siamese network, build your own latents, right? BYOL and so on, right? So these are all self-supervised methods, and we also compare with FedAVG AE, which, like I mentioned before, is a federated averaging on autoencoders, right? And also single client. That is, we say that there's no federated learning. Then what happens, right? So the client has its own data and it trains, right? In fact, that does quite well, at least for linear evaluation, and we managed to show this. We also actually showed, I mean, at least we give values for our own method for an extreme case where just 2 classes were there at each client. And in fact, we showed that our method is it doesn't do the best, but it is it's quite stable even when it gets information about just 2 classes. Okay, so now I'm going to show a few plots. I'm not sure if you'll exactly appreciate these plots, but I think it at least gives you a good understanding of how to really evaluate such methods. This plot is about accuracy versus the communication rounds, and we are comparing different baselines here for both data sets, right? So we are clearly beating all the other methods. But more importantly, what really helped us is the fact that we converge faster, right? So, of course, there's no free lunch, right? So we do share a lot more information as compared to many other methods, right? We share the latent space representations of all these data points. So which means that we share a lot more information, but we are also getting gains because of that, right? So that's what this plot is showing. I actually wanted to showcase that, in fact, we are getting faster convergence using our method. And this is about average global and local accuracy. Local accuracy is important because remember, we never really shared the weights and averaged them, which means that we actually have different machine learning models, right? Different representation learning models at each of the clients. And that is why essentially our method is personalized by design itself. But is the personalization good enough, right? So we did not really bring in any personalization goals in terms of losses. But turns out that personalization is sort of fairly good. It's doing well on the local test data. But there is still a little bit of inconsistency. But yeah, that's something now we should think of improving. Yeah. Another question is, how robust is your method to local epochs? So this was the aspect I was talking about initially, where I said that there's going to be this trade-off, right? So sometimes it may so happen that you want to actually do many more global rounds to improve generalization capability. So you need your method to do well, even if you're running only one local epoch every time, right? On the other hand, a communication overhead may be so large that you may need to run 10 local epochs and only then exchange or go for global global updates. So it turns out that we are quite stable across the number of local epochs, mainly because of the convergence. Okay, because we're able to converge faster. It turns out that even with be it scalability or epochs, right? Epochs is actually talking about fast convergence itself. We are able to see that even at epoch equals 1, we are actually getting quite a good accuracy number. On the other hand, this is a t-SNE plot. I must mention here that so typically communication cost is a reason why one would not want to go for complex models. But here it turns out that I can increase my model complexity, but I can keep the latent space vector to be slightly smaller. So in fact, it's latent space vectors that dictate the communication cost. So that was one exciting aspect of this work. And in a way, we think that this is a novel line of work because communication is efficiency also can be prioritized over privacy. Okay, so if there are applications where communication efficiency is more crucial, then this could be one of the preferred methods. Next, we are looking at federating VAEs as well. That's actually far more exciting for us as compared to just AE. AE is still a very simple model. There's not much you can play around with, but VAE has this aspect of uncertainty, which truly helps in assessing how federation has worked. So thank you. Thank you for giving me the opportunity to talk. And yeah, I think I'm open to take questions.
Yeah, thanks a lot, Dr. Ranjitha.
Right.
So we have few Q&A questions which is shown out here.
Okay.
So
somebody is asking me, I'm able to read it. Yeah, MNIST with 10 classes or feminist with 62 classes. Frankly, MNIST with 10 classes. So with 10 classes, we easily get about okay. So yeah, sorry. MNIST with 10 classes, I don't recollect. So I don't recollect both of them. FMNIST, I think this is feminist. Okay. No, we've feminist we have not tried. MNIST we have tried, but I don't recollect the numbers. But we have a blog coming up on this, so hopefully we'll put up some more numbers in the blog. Okay. Using a decoder, can the latent space that is shared be decoded and compromise privacy? So so this person is asking if you can share the latent space. Okay, so yeah, can it be decoded? So in fact, that is one concern. Perhaps if you can actually try over many decoders, one representation is possibly the true representation, right? The true data itself. But it's not necessary that happens every time, right? I mean, the decoder that gets trained does not really, it does not actually have X hat to train to get the exact same decoder. So that's why we said that we go to a latent space at the server, which is called as Y. If the server really had, I mean, if it had the knowledge of, so basically, if there was a loss that was comparing Y and X, then I agree. It is possible that it could compromise privacy. But because that's not available, I don't think it compromises privacy. Okay, so since the server has no control over the input the client may feed, isn't there would be long tail distribution problem of entirely unknown latent representation? Yes, Vinay, I think that's where actually it helped us when we did pre-training. Okay, so it actually helped us to start off at a point where where the encoder was already guided slightly. So frankly, when there's absolutely no input, we did face a lot of problems. So I agree that when there's no control at all, it's tough to actually converge here. Yeah. Is there a security threat sending the latent? Could someone recover it? Yeah. So Renam, I think, I answered that question. It is indeed a security threat, right? If your privacy is the biggest constraint, then I would say that encrypting the latent space is a better idea. Many methods are available. In fact, in our paper, we cite many methods where encryption of this latent space is also one of the ways out. That's why in my last slide, I actually said that if you have applications where communication efficiency is your priority as compared to privacy, that's where these methods could actually work well.
Okay.
Yes. Yeah, I think most of them.
Yeah. Thanks a lot, Ranjitha. I have one question from my side.
Sure.
Do we have any real-time kind of federated learning system being deployed in the market currently? Do we have any products like that?
Market, I mean, internally, I think a lot of companies have done it, right? Google already has something. I mean, I know for a fact that many NLP-based models have been deployed. I'm not getting the names off the top of my head, but I'll try to give you the information. So I think you also, we discussed about Apple's method. So internally, there are plenty. If you talk about platforms, Intel has come up with this open FL framework, right? So there, that's actually open. So you can actually take and code up there, and it's very much available for implementation. So I think internally many companies have done it. The ones that are open are few of them, which which we know of. Yeah, and otherwise I'm not very sure. Otherwise, yeah.
Okay. Yeah. Thanks a lot, Ranjitha. Once again, thanks a lot for this wonderful presentation on federated learning concepts, especially on unsupervised federated learning here. Thanks, Ranjitha. We'll go ahead.
Thank you so much. Thank you, actually, Pragya, for the invite. Thank you, Sendil, and thank you, Olga. I've troubled you guys a lot, so thank you.
That's fine. It's a pleasure for us. Yeah. So we can go ahead.
So somebody has asked, do you have a publication of this work? Actually, we have submitted somewhere. Getting things accepted is not so easy. We are also struggling. But hopefully in another 2 months or so, this should be on archive at least. Yeah. Thank you so much.
So we,
okay.
Yeah. So I would like to thank our, sorry.
Should I share the other slides?
Yes. Yeah. We'd like to thank again our executive strategic partners. Next slide, please. So can we go to the slides? We have.
Sorry about that.
Oh, okay. Sorry.
Right.
Yeah.
Did I?
Yes, we can go ahead. Ahead. So, next slide. Yeah. We'd like to thank Qualcomm AI Research. Next slide. Syntion. And our platinum partners, Sony. Gold strategic partners, Analog Devices, ARM, Edge Impulse, and Infineon. Inatera, Microsoft, Renesas, ST Microelectronics, Synaptics, and our silver strategic partners AZIP, Arduino, Branch, Efficient, Greenway Technologies, Gravity Incorporation, Himax, IBM, Magimob, Nota AI, NXP, Poly Technology, QZO, Schneider Electric, SensiML, Silicon Labs, TTK. Next slide. Yeah, we thank all the participants for their presence and also the Q&A sessions. Thanks a lot, both participants and also to Dr. Ranjitha Prasad and to our strategic partners. Thank you all.